Welcome back to Differential Calculus. In this video, I want to introduce you to Riemann sums, which are going to tie the discussion we've just had on summation notation and area back into functions. Let me get my head out of the way and I'll show you what I mean. So let's consider for right now the graph y equals f of x, which is increasing on the interval from a to b. To make this work, it doesn't have to be an increasing function, but the increasing function will tie the language back to what we've been talking about recently. So a curve that looks something like that, and maybe here's A and here's B. I want to find a tool for calculating the area of this space, bound above by y equals f of x, bound below by the x-axis, and to the left and to the right by the boundaries x equals a and x equals b. And just as we've seen before, we can do this by trying to come up with some sort of a rule or formula for the area. And just as we've seen before, there are two options. To show you what I mean, I'm going to first give myself a little bit more space here so I can fit everything on the screen. Doing my best to line this back up with the grid. And let's copy this thing and paste it so I have two copies. Why did it only give me the one bit? I don't know. Let's try that again. Copy this whole thing and paste it in so that I have two versions to draw. And I'm going to do this by method of lower sum and upper sum, although the words are going to mean something slightly different than when we saw them last. I'm going to divide the region that I care about into vertical components. Just by the nature of where I've drawn the grid and where I have these points on the grid, it makes sense to divide it up into 5 regions. For the lower sum, I am going to draw horizontal lines on the left side of each grid mark. For the upper sum, I'm going to draw horizontal lines on the right side. So that's why in this context, instead of seeing the words lower sum and upper sum, sometimes you will see these described as the left sum and the right sum. But the ideas are going to work the same as they did before. My lower sum has underestimated the area in every single bit. Right? There's all of this bit in all of these triangles that is underestimating the area. My right sum is overestimating the area. And the actual area is going to be somewhere in between. I'm going to focus on the upper sum in this video, because that will make the arithmetic a little bit easier. And in order to do this, I'm going to draw the same figure, but really zoomed in and exaggeratedly. Right. So we again got some curve going on. We've got A, we've got B, and we divided up into a couple of regions. Hopefully I did this and counted right. No, I was off by 1. That's okay. I can just do a quick regendectomy, get rid of the bits we don't need. There we go. That's a little bit closer to correct. Let's put this... Well, why did that come back? I thought I got rid of that. There we go. Let's put this B closer to the endpoint over there, and we'll pretend I drew it that way in the first place. I have taken my area and divided it up into rectangles. The width of each of these rectangles is the exact same value. I'm going to call it delta x. And of course, delta x, the distance from A to B is just B minus A, divided into n intervals. So each of those intervals is B minus A over n. And I'll shade these in alternate diagonals. To kind of get the picture. The endpoint between these first two is at the point A plus delta x. The next endpoint is at A plus delta x plus another delta x, so that's A plus 2 delta x. And kind of an odd thing to mention here, but I do want to point out that the right endpoint B itself is A plus n delta x. Go ahead and plug in that expression for delta x and verify that yes, that is just a really complicated way of writing B. And the reason that I care about that is the right endpoints tell me where the height is, right? The height is determined by the right endpoint. So this is f of a plus delta x. The height here is f of a plus 2 delta x, and so on. Now I'm looking for the area. I know that the height is f of a plus delta x. I know that the width is delta x. And I am intentionally leaving some space here, which might be important if you're trying to copy down with me. The area here is f of a plus delta x times delta x, right? The area of a rectangle is the length times the width. But each of these rectangles has a different area. We have 1 delta x, we have 2 delta x, we have 3 delta x, and so on. In general, I can call that f of a plus k delta x. That was supposed to be in yellow. And to find the total area, I can just add these all together. The sum, k starts at 1 and goes to, well, I used little n here. To get the left sum, the lower sum, I would just have to change my starting and ending point, right? If I wanted the left sum, I would start at a. That's k equals 0. And I wouldn't have to go all the way to n, because the last one wouldn't matter. I'd have to stop here, which is n minus 1. For the sake of convenience, summations k going from 1 to n are easier to evaluate, so those are the ones we're going to use. But the left sum is just k goes from 0 to n minus 1. And I do want to point out, before I get into actually doing an example of this, because I assumed that my function was increasing, the lower sum underestimated the area, the upper sum overestimated the area. If I had a function that was decreasing instead, then when I divide it up, the lower sum will be the one that overestimates the area. And the upper sum will be the one that underestimates the area. But the point still stands. If you have a region where there is a function that is increasing, the lower sum and the upper sum will bound the area. One will be high, the other will be low. If a function switches from increasing to decreasing, the rules will switch between those regions, and we can figure that out a little bit later. For right now, let's just focus on how to calculate this. And I'm going to start off with a very simple example. F of x equals 5 on the interval from 1 to 4 with n equals 6. And the reason that I wanted to start off with this example was to illustrate that there's nothing new happening here. Right? The area under f of x equals 5 on 1, 4 is a giant rectangle. The distance from the left to the right is 4 minus 1, which is 3. So I know from basic geometry that the area of this region had better be 15. As you'll see in the video, or in the problem I asked you to look at the end of the video, getting the exact value is not necessarily going to happen, but we should be able to get reasonably close, and we will get the exact value this time. Being able to handle the weird cases is important, but in order to make the computations easy, we're going to look predominantly at the simple cases in this course. But I want to try to solve this problem using Riemann sums, because I want to get used to the definition of Riemann sums. A is 1, B is 4, which means that delta x is b minus a over n, which in this case is 4 minus 1 over 6, or 1/2. F of a plus k delta x is f of a is 1, delta x is 1/2, so this is 1 plus 1/2 k, but that's actually not that interesting in this case because it's just the constant value 5, but thinking through that, right? A plus k delta x. A is 1, delta x is 1/2, k is going to just still be there. And then the definition of the Riemann sum says that the area is approximately equal to the sum. K starts at 1 and goes to n, which is 6 in this case, of f of a plus k delta x, which is 5, times delta x, which is 1/2. This is a really easy summation. The sum of a constant is that constant times n. 5/2 times 6 is 15, which is exactly what we said we were going to get when we started. As one more example, let's take a look at the function f of x equals 4x minus x squared on the interval from 0 to 4. If I jump over to Desmos real quick, you can see that the graph in this case is a parabola. And in the interval, x going between 0 and 4, this graph actually perfectly bounds a region between the graph and the x-axis, and that's the region we're going to be trying to figure out. I'm going to specifically look at the case where n equals 10. All right, so delta x is b minus a over n. B in this case is 4, a is 0, n is 10, so delta x is 2/5. Our function is going to be f of a, which is 0, plus k times delta x, which is 2/5, or just f of 2/5 k. Right. Plugging that into our function, that means we have 4 times 2/5 k minus 2/5 k squared. All told, that's 8/5 k minus 4 over 25 times k squared, which would make a lot more sense if I had put the squared on the right space outside of the parentheses where it belongs. Now, our area is the sum. K starts at 1, goes to n, which in this case is 10, of our function 8/5 k minus 4 over 25 times k squared times delta x, which is 2/5. We can distribute to get a really ugly looking fraction. But by doing that, now all of a sudden we are taking the summation of something that is linear, so we can split it up. and use our summation rules. Right? N equals 10 is small enough that we probably could have just written this out, but I think it's good practice to get accustomed to using the summation rules. Right? So sum on k is n, 10, times n plus 1, 11, all over 2. Sum on k squared is n, 10, n plus 1, 11, 2n plus 1, 21, all over 6. My calculator is very happy to tell me that if I have 16 times 10 times 11, that is 1,760. If I have 25 times 2, that's 50. And if I try to do this division, it does not work out evenly. So let's go ahead and just reduce by dividing by 10, 176 over 5. Right? Same thing for the second one. 8 times 10 times 11 times 21 comes out at 18,480. 125 times 6 comes out at 750. I can see that there's that nice divide by 10 option available. I think that there's a 3 as well. Yep, that works out. And it comes out at 616 over 25. All right, multiply this first fraction top and bottom by 5. So 5 times 176 is 880 over 25. And then 880 minus 616 is 264 over 25. All right. I've left our result here as a fraction, as an exact value, as something I like to call an answer only a mathematician could love, because this is math class and that's what we do. For practical purposes, though, you're going to just do the division, and you probably would have done it way up here, not waiting until you get down to here. But 264 divided by 25, my calculator is happy to tell me, is approximately, or is exactly, but I'll use approximately anyway, 10.56. Usually on a problem like this, I will ask you for an exact value, which means I want the fraction. But being able to get the approximate value, the decimal value, is also useful. We're going to look in the future at ways of finding the exact area, and comparing our decimal area to the exact value is something that can be interesting and we'll come back to. For today, though, I'm going to end with one for you to take a look at. I don't know why I'm about getting my head out of the way. F of x equals 5x minus 2. F of x equals 3 minus 1/2 x on the interval from 0 to 6. The first thing I want you to do is to graph this function. Recognize that the graph can be easily calculated using geometric figures, and do that. Then, and more importantly, approximate the area using an upper sum with n equals 12. You will find that you get different values on each of these. The first one is going to give you the exact value. The second one is going to be slightly off. And so again, it brings to mind the question, why are we taking all this time to do a lot more work to get a less precise answer? And again, the answer to that question is that we're looking at the easy problems today, and we're making sure that we understand how the process works for the easy problems. Because the hard problems are not things that you can do pencil and paper, and trying to figure them out without having the background of how to deal with the easy ones is just that much harder. All right, so it's good practice. I would never actually use this process for this particular situation, but it is good practice for the future. Take a couple of minutes, see what you can do with that, and I'll see you in the next video.